Hello and thank you for watching our video. Many thanks to the chairs and organizers of Photons plus Ultrasound for allowing me to give this talk, at least as a video. Unfortunately, we can't meet in person in San Francisco, which I really would like to, but maybe in June in Munich at the European Biomedical Optics Conference this could be possible. My topic is Photo-Acoustic reconstruction from photothermal measurements. This work is the output of an Austrian cooperation with Gregor Tomera and Günther Meyer from the University of Applied Sciences in Wales and with Markus Haltmeier from the University of Innsbruck. The Research Center for Non-Destructive Testing and Biomedical Imaging, where I come from, is in Upper Austria, located between Salzburg and Vienna in Linz. My topic for today is to perform photoacoustic tomography using an infrared camera as an image detector by measuring the temporal and spatial variation of the surface temperature. Then calculating a virtual acoustic wave from the measured temperature, and finally perform acoustic reconstruction on that. This combines the advantages of tomographic imaging and of ultrasonic imaging. In tomographic imaging, we have more than 1 million detector elements and it is contactless method, but it shows a lot of blurring if you go to a deeper imaging depth. In acoustic imaging, you have much better resolution, but only about 100 detector elements, and it's a contact method. You need some coupling media. Let me give a short outline of my talk. First, I will give an example of a laser-generated thermal acoustic wave field in comparison. Then I will show that you have a local transformation between the measured and the virtual temperature signal. This is called the virtual wave concept. The thermal point spread function, that's the resolution what you can gain for tomographic imaging. And by adding additional information such as positivity or sparsity, we can show that we can gain much higher resolution. This will be shown on an experimental example with graphite bars in an epoxy resin. In the beginning, we compare the temperature field and the pressure field when we heat an aluminum block with a Gaussian laser. First, the light is absorbed at the surface and the temperature field evaluates by diffusion of the heat. Then we get by thermal expansion an elastic wave, a photoacoustic elastic wave, which can be also shown here. You see here the heat diffusion and here the acoustic wave, and both are generated from the same initial temperature distribution. So the temperature field and also the acoustic pressure field come from the same source, the heating of the material by a short laser pulse, and therefore it should be possible to calculate the acoustic wave from the measured heat or the other way around. Now let's explain the virtual wave concept. The photothermal heat diffusion equation gives from a given temperature T0, the heat diffusion and the evaluation of the temperature T. The photoacoustic or pressure wave equation gives from an initial pressure distribution P0 the evaluation of the pressure P as a function of time and space. But of course we know that the initial pressure distribution P0 is just proportional to the temperature heating for a short pulse, and this temperature increase is proportional to the initial pressure. And now, that's the essential point, we define a virtual wave with the same relation between the pressure and the virtual temperature T for all the time. So the equation, the virtual wave equation for the temperature T vert is an acoustic wave equation. So you can use acoustic reconstruction, but the virtual temperature wave has the units Kelvin and can be calculated locally from the temperature evaluation. This local transformation between the measured and the virtual temperature signal is shown here in Fourier space. We take again the equation of the thermal diffusion, the first one. The second one is the equation for the virtual wave, for the virtual temperature, which is an acoustic wave equation. In Fourier space, we get the Helmholtz equations here for the temperature in Fourier space, the delta, and the virtual temperature, the delta vert. And you see they look very similar, and you can get from both equations that the virtual wave and the real wave, the measured, are just connected by this equation. If we Fourier transform this equation back to the real space, we get an equation between our temperature T, the measured temperature, and the virtual temperature here. And this kernel K has the sound velocity, the virtual sound velocity C, and also thermal diffusivity alpha inside. So it shows the relation between heat diffusion and the acoustic wave propagation. The result is that the T vert is the one-dimensional reconstruction at each pixel location R. It's a local transformation because you have the same location R here for the temperature and the virtual wave. It can be discretized to produce a matrix equation. T is K times T vert, where T is the vector of the temperature for all the time, and T vert is the vector of the virtual temperature in K is this matrix here. If you measure the temperature T and you want to calculate your virtual temperature T vert, then you have an inverse problem, an ill-posed inverse problem, and you have to use some regularization methods to solve that. Here we have used the truncated singular value decomposition method to invert this problem. The reconstructed signal Trec was calculated as an estimate of the virtual wave from the thermographic signal T. I do not have the time to go into the details, but I will show how this works on a small example. We have three temperature sources which are heated at time 0. You see here the T naught at the function of the depth and of the surface. It's a two-dimensional example. Then the surface temperature is measured as a function of time. You see from this heated spot the heat diffuses very fast to the surface and the amplitude is quite high. From this source it takes much longer and also the amplitude is rather low, and this temperature signal you can use to calculate locally the virtual wave. And you see the virtual wave already shows some acoustic wave behavior, and what you also can see here is that if your sample is deeper, then from the truncated singular value decomposition you get more blurring than for the temperature sources which are very near to the surface. And you can use these virtual wave signals with some acoustic reconstruction methods like the Fourier synthetic aperture focusing or the time reversal techniques to calculate the initial sources T naught. To avoid the blurring of deeper lying structures, we can use additional information for our regularization and for our reconstruction. One possibility is to use sparsity. That means that we only have very small sources compared to the whole sample volume. Another a very important source of additional information is the positivity. Of course, if you take a pressure signal, then it's even if the initial pressure distribution is always positive, then the pressure signal itself is not positive. It goes also to the negative values. But if you take the integral and integration of time, what's shown here with this m, then you will see that it's something like the velocity potential of an acoustic wave, and this velocity potential is always positive. If you take this m instead of the t word, then you have a positive signal and you can use this for regularization. And now we have used both the truncated singular value decomposition method, where we reconstructed our signal mrec as an estimate of the m word for the thermographic signal, but we also have used the so-called Douglas-Redford splitting method, where we have minimized this term. You see this first term is the data term, where we fit our measured temperature T, and the second term is an L1 term, which introduces a sparsity, but also that we can take the positivity into account. Now let us show how this virtual wave concept works on experimental data. Here we have used the laser, shown here, which heats via this mirror a specimen. And the heat from the surface of the specimen went through this mirror because this infrared camera has a sensitivity only between 3 and 5 microns, so very long wavelengths. The specimen consists of 3 graphite bars at a different distance to the surface, which are embedded in an epoxy resin. And this epoxy resin is opaque in the infrared range, so with the thermocamera you measure really the surface temperature. So what you can see here is the laser. The laser heats these graphite bars, and the temperature on the surface is measured with this infrared camera. Here you see the function, the temperature is a function of time. From the bar which is very near to the surface, again the heat goes very fast to the surface. From the bar which is very deep inside, the heat takes very long, and also the amplitude is quite low. And let's take the signal here from that pixel. You see it looks like that, and you can use this virtual wave reconstruction to calculate the virtual wave out of that, and this is a very clear acoustic signal what you see here. You can do this for every location, for every pixel of your camera, and what you get is a virtual wave like that. Now we have used these virtual waves to reconstruct the initial temperature distribution. The top you see an ideal virtual wave, so without any blurring from numerical simulations. And if you take these virtual waves using FSAFT, you can reconstruct the initial temperature field quite well. You see these 3 spots. If you take the truncated singular value decomposition, which takes not into account the additional information of sparsity or of positivity, then you see that the virtual wave is rather blurred, especially for the deeper structure. You see that the blurring is rather high, and if you do the FSAFT reconstruction from that virtual wave, you see that the deeper structure has a very low amplitude and you get rather high blurring. If you take additional information like sparsity or positivity into account, then you can see that you have a much better virtual wave. The blurring is not so high than with the truncated singular value decomposition, and the reconstruction using the f-SAFT with this virtual wave, you see that the reconstruction is much better and the spatial resolution is much higher. Let me sum up. The virtual wave concept allows the application of ultrasonic reconstruction methods for active tomography data. It gives a simple and intuitive representation. You get an A scan and a B scan from tomographic data, and the virtual wave concept enables a 3D reconstruction of the internal structure of the observed specimen. Last but not least, it allows incorporating prior information, which significantly improves the quality of the regularization and the reconstruction. Let me acknowledge our funding agencies, and with the last slide, which is from Salvador Dali, The Persistence of Memory, I would like to close my talk. It always reminds me that we have to fight entropy. Thank you for your attention.